So we are going to do Benford's law, a goodness of fit test on Benford's law. Did we do it last time? Yes, we did it using StatCrunch. I'm going to show you how to do it using SPSS and take a case where we will actually not reject the null. Last time we rejected the null in the sense whatever data that we had did not fit the hypothesis that the categories were equal. In other words, the transaction digits were equal. In reality, Benford's law suggests whatever digits you have, if you have one, it will just go down. It will have a right skew. Start with digit 0, 1, 2, 3. So as you increase in value, it will decrease. That's Benford's law. Clearly, they're not equally likely. So go on and open the file that we had last time, which I believe, or import the file. Benford.csv. So we have two variables. One is the transaction that took place. The other is the leading digit of the transaction. So digits, of course, go from 1 through 9. Now we want to see as to what the histogram looks like. So you can go to graphs, legacy dialog, select bar. It's in simple, leave it as is, and hit define. So don't do the transaction because that's of no value to us. It's just transaction index. We want to look at the leading digit. So move it to the category axis, which would be the x-axis. And that's all we need to create a simple bar graph. I'm going to treat all of these values as nominal or categorical data and put it in category axis. And hit OK. And you should see that. Now, if you look at that, do you think that the digits are equally likely? Absolutely not. And we came to the right conclusion last time with StatCrunch. They weren't equally likely. The digits have different frequencies. We rejected the null, and we concluded that the categories aren't equally likely. Clearly, the data doesn't follow a histogram when things are equal or categories are equal. So we have to still test. Go to analyze, to non-parametric tests, because chi-squared is a non-parametric test. Over to legacy dialogs. With chi-squared. And again, transaction variable is useless. It has no information, it's just transaction ID. So we want to test for the leading digit. So going to click on leading digit and move it over to test variable list. Good. And just like StatCrunch, we're going to say all categories equal for now. Now, what do we expect to get? It should say, should it reject the null or not reject the null? Reject the null, because the null is that all categories are equal. The alternative, all categories are not equal. clearly from the picture, the categories are not equal. The leading digits are not equally likely. It has a right skewed distribution. So I'm going to keep the expected values as all categories equal. And that is the report that you would get. This particular table that you see here, it's exactly the same thing that we had previously with StatCrunch. Down below is the chi-squared value, the degrees of freedom, and it says async. That simply is the p-value. It stands for asymptotic significance. SPSS calls p-value as sig, because that's the significance. Asymptotic significance is an approximation. So if I give you an SPSS report, don't look for p-value. You have to look for sig, because sig and p-value are one and the same. So in total, we had 130 records, and according to the test, the null is not true. The leading digits are not equally likely. Chi-squared is 69.938. Take note of that large value, put a star, and that will lead us into the next section. Good. Now, those are the Benford law percentages. So the relative size of each of them would be 30.1, 17.6%, 12.5%, and so forth. How did we find expected counts for a regular chi-square test? If we had probabilities, how did we find the expected counts? What did we multiply the probability by to get the expected count?
Row total by the column total?
Well, that is for a chi-square test. I'm talking about a chi-square goodness of fit test.
Oh, you divided it by like how many like cases or like.
Well, if I divide, I'm going to get the probability, right? I want to multiply by the probability to get a certain count. So last time when it was equally likely, it was 25%. So we took something and multiplied that by 0.25 and rounded it to the nearest,
total.
the total. In our case, the total is 130. I want you to multiply or find 30.1% of 130, 17.6% of 130, and write the counts that's rounded to one decimal place, and tell me what those counts are. Those would be our expected counts. We have the expected counts. Do you believe that the expected counts sort of follow the observed counts in this picture? No, maybe. This is what we observed. That is the expected. I showed you the graph. Do you believe that this nearly follows those?
No.
Yes? So if I did a goodness of fit test with a null hypothesis that the observed counts or data follows Benford's law counts, the alternative data does not follow Benford's law counts. Last time we rejected the null because our null last time was that all categories were equal. This time it is a different null. My null is that the data is going to follow Benford's law. The alternative, it is not going to. Let me ask you, based on the picture that you see, should the test reject a null?
Yes.
Reject a null and conclude that it does not follow Benford's law?
No, because it does follow.
If you look at that curve, it's not perfect. What we have in SPSS matches up. If you flip it, sort of right skewed data for Benford's law. It is not perfect, but it is close. We just want to know if it is statistically significant. The claim is that the transaction digits, leading digits of transactions, follow Benford's law. Let's see. We can go back to analyze, non-parametric tests, legacy dialogues, chi-squared. And everything is as this, but only this time, instead of calling it as all categories equal, I am going to enter the frequencies, starting with 39.13. So enter 39.13, hit add, 22.88, add, 16.25, add, repeat the process, and we're going to enter all counts. The last one is 5.98. And that's what we have. Those are the observed values. Those are the expected values. What's your name?
Mona. Mona.
Lorna?
Mona.
Mona. As Mona mentioned, they are very close to each other. 39, 39.1, 24, 22.9, 6, 6.6, 7, 6.0. They're not exactly the same, but they are close to each other. But statistically, are they different or are they the same? The chi-square test statistic is 7.204. The significance is 0.515. Is the p-value of 0.515 less than the alpha of 0.05? 0.05 is 5%, 0.515 is 51.5%. No. So we should not be rejecting the null. So the transaction digits do follow Benford's law. Does that make sense? Which was quite obvious from the picture also, but we can't just look at the picture and say, oh yeah, it follows. We need a statistical basis, and there it is. Good.